All right, so in math and physics, one of the things that we often look for is when we use a matrix on a vector and the vector remains essentially unchanged. So if I have some sort of matrix, A, operating on a vector x, and the result out is just a scalar multiple of x, well, we like this in math and we find it interesting. And this k value would be what we would call an eigenvalue. So if we think about this equation, for this to be true, what we're looking at is A is a square matrix, so A is n by n, and x is a column vector, that is, so x is going to have n rows and one column, and k, or lambda, we normally use lambda actually, so let me make this lambda, is an element of reals excluding 0. So 0 obviously would be the trivial solution. If A was 0, lambda would be 0. So our eigenvalue, so lambda is the eigenvalue. X then would be the eigenvector. Okay, so looking at this equation, we could solve it to explain how we get our eigenvectors, our eigenvalues. So solving this equation, I would have ax minus lambda x equals 0. If I factor out my vector x, I would need to factor it out to be a right multiplication. And to take a matrix A and subtract a value of lambda, I would need to multiply lambda by the identity matrix so that I can do the subtraction because I need the same dimensions. That would be equal to 0. So this equation is going to have a solution. So this implies that the determinant of my new matrix, A minus lambda I, is equal to 0. So this is the equation that I end up solving. And this equation is what we call the characteristic polynomial. So notice that this is an n by n matrix. So my characteristic polynomial is going to be an nth degree. So think about a 2 by 2. If I was looking at the determinant here, the most I would end up with is a lambda squared. Yeah, and that would come from a lambda being here and a lambda being here because I'm subtracting lambda I. So I would only have lambdas along the main diagonal. So I would have a degree n